random and noise. Let's begin talking about how to generate noise using the frag function and the sine wave. The frag function is equal to the remainder of the division by 1 or the modulus operator. As you can see, it returns the peaks of the sine wave. If we multiply the sine wave by a fairly large number, we can see that the wave begins to deform so much that it becomes more like noise and no longer looks like a sine wave. This result can be used as one-dimensional random function. Working in 2 dimensions, we can use the sign of the dot product of an arbitrary vector. It produces an excellent result, this way obtaining our next 2-dimensional random function. Here you can see the result of applying the 2-dimensional random function. Do you remember how the smooth step function works? To begin with, let's check the previous function by extending in the x-axis. Notice that we obtain several random points. Let's look at the next graph. If we do an interpolation between the random points, we get a kind of polygon. Furthermore, if we apply the smooth step function inside the interpolation, we get smooth curves. Value noise works with cells. Each cell has 4 corners, and for each corner there is a random value using the random function that we defined before. Essentially, it is an interpolation between the random points using a cubic function from the top left to the top right, then from the bottom left to the bottom right, and finally an interpolation from top to bottom. Although the result is not the best, it can be used as a basis to create more complex noise, and it has a low computational cost on the GPU. Perlin noise is perhaps the most famous, named after its creator, Ken Perlin. It is very similar to the value noise, but the interpolation is made between random vectors and not just float numbers. The first part is the function that returns the random vectors using a matrix to simplify the calculation. Then it normalizes the result vector. Next, we get the 4 random vectors, and in contrast to the value noise, it uses the dot product to obtain a value between the corner and the current point. At the end, an interpolation is made using a quintic function, and the result is much better than value noise. I use different sources for the shaders inside the GODOT project, but the key points are the same. As you can see, there are the vectors, the normalization, and the dot product applied to the vectors. And finally, they are mixed. Simplex noise is an improvement of the initial algorithm by interpolating between triangles instead of squares. This is much more efficient than the original algorithm, and here are some of the differences. You can check how the grid works in the book of shaders page. You can see in these lines the conversion from a grid of squares to a grid of triangles. Cellular noise is based on distance fields, the distance to the closest one of a set of feature points. To avoid unnecessary calculations, we divide the total space in cells. Then we only take into account the point of the initial cell and the points that are inside the adjacent cells, a total of 9. Here is the example of the cellular noise. First we have the random function, then the variables to draw the grid, next the for loop that is used to make the search in the 9 grids, the points that are defined randomly, the animation with the sine function, the variable that keeps the difference between the position vector and the current coordinate of the UV, and finally the distance field to draw the cell. This graph is an example of multiple iterations or additions of a sine curve. quite similar to what happens with fractal Brownian motion, but instead of using iterations of a sign function, we use noise, as you can see. Once again, we are on the page of the book of shaders. Here we have first the random function, then the grid drawing, followed by the four corners defined by a floating random number and the interpolation of these corners. Now the function FVM uses several iterations of the value noise using a for loop. We apply it several times. These iterations are called octaves, and the more iterations are applied, the better the result obtained. Of course, the higher the number of iterations increases the load on the GPU. The last noise implementation we're going to discuss is domain warping. It's about deforming the UV space using several iterations of FVM. First, we apply FVM to both axes of the UV map, and then apply FVM again to the resulting vector on its two axes. Finally, FVM is applied one last time. Using the time variable, we get animation. Of course, this effect is quite expensive. So we're back in GODOT, and here is the result of the different types of noise. Finally, the last remaining task is to verify that GODOT has all these options integrated in the form of a texture. Here I'm going to use standard material, then the noise texture. I select noise, and as you can see, we have all the options available: Simplex, Simplex Smooth, Cellular, Perlin, Value Cubic, and Value. Below we have the option to apply FVM, which was already the default and was affecting the final effect. You can see that Cellular is quite similar, just missing the animation. FVM I can affect the octaves, and we have domain warp, which has several options. Just keep in mind that domain warp is the combination of all algorithms and is quite demanding on the GPU.